Hello everybody, this is a short intro to the rotational motion lab this week. So it's rotational motion, P&W. When you log into Pivot you'll see that, and let's take a look at it. So we're going to use Newton's second law for rotation to experimentally determine the moment of inertia, sometimes called rotational inertia, of a bicycle wheel. To do this we'll measure angular acceleration, torque, and we'll experimentally come up with the moment of inertia, and then we can compare this to a theoretically determined moment of inertia, and we'll see how close they are. To get the theoretically determined moment of inertia, we'll use a table in Chapter 7. There's a table of different symmetrical shapes. Now there's not one exactly for a bicycle wheel, so we're going to get an approximate answer. So don't be surprised when our theoretical value and experimental value don't equal each other exactly. More about that in a bit. Okay, so it looks sort of like this. Here's the video that we have down here. And there's several different bike wheels. We're going to actually choose Spinergy Z Lite. So we'll click on this one. Keep the hanging mass at 20 grams, and we'll load this up. So this is more of a typical bike rim that you're probably used to. If you notice, there's a mass here on the right hand side of the wheel. This is a 20-gram hanging mass, and it has a string that goes all the way around here to somewhere over here. So when the person here cuts this string, the wheel will be free to rotate. So you can imagine if it was a heavier wheel, it wouldn't rotate as much. A lighter wheel would rotate a little easier. The shape of the wheel and the mass really determine how easy or hard it is to get this to rotate. So when we say moment of inertia or rotational inertia, it's really a measurement of how easy or how hard it is to get this shape to rotate. Let me just play the video so you can kind of see what it looks like once this is cut. Okay, I'll just hit play. It's cut and it starts to rotate. So we're going to analyze the motion from the moment that it's cut. So when the moment that it's cut, the initial angular speed is 0. So right after it's cut, and we're going to analyze the motion up until the point where the mass hits this little table down here. So we don't want it to hit the table. We want it to be right before it hits the table. And we should be able to get about 6 different data points from this. Let me back it up a little bit. And I'm just going to advance it frame by frame. You can do that by hitting the this button here. Advance, advance, and again, I don't want I want it to get to the point right after it's cut. Okay. Oh, there we go. Could even maybe back it up a little bit so you can play around with that a little bit. Grabbing the slider and moving it back a little. Oh, that's pretty good. Right there. Okay, you can see that it's cut there. We've got some tools we can use. Whoops. Let me click that. Here's a wheel. I can line this up. And it looks like we are starting here at this spot. I also have a ruler I can use. And you can rotate this in different directions by grabbing it here, moving it around. We'll be able to use that, and we've got this stopwatch. So right now I want to set this to begin at 0 time. So if you just click here, notice right now it's at 0.27500 seconds, frame 66. I'm going to reset this. So right now this is at 0 seconds and 0 degrees. And I'm just going to be able to measure this going this direction. Technically, if this is rotating clockwise, that is the negative direction, but I'm just looking at the magnitude of angular displacement here. So I'm going to let this rotate until I get to 15 degrees, 30 degrees, 45, 60, etc. Again, just keep in mind I do not want this mass to hit the ground. I want to take data before that. Okay? So right now, again, it's 0 degrees, it looks like. It looks like I'm using this spoke as a reference point. So 0 degrees at 0 seconds. I can come down to the data table here and start filling this out. So delta theta, 0. You're going to have to calculate it in radians. More about that in a minute. And then time in seconds. So 0 and 0. And then I can advance this until I get to 15 degrees. Pick whatever you want, but I'm going to pick 15 degrees. So you're going to have to do a little bit of estimating here. All the way from this mark to this mark is 30 degrees, so I want this spoke to be about halfway in between those. So I'm just doing it slowly. Again, if you want, you could grab this and move it. I was doing it pretty slowly, but let's see. Again, this was 0. This is about 15, and you can take a little bit more time and do it a little more carefully. But it looks like about 15 degrees. It's rotated 15 degrees, 0.6167, 0.61667 seconds. So then I can come here, delta theta. Okay, I'll just do this. This was 0. This was 0. Now I have 15 degrees, and then you can record the amount of time. Again, 0.61667, 0.61667. Verify that. Don't want to make any random errors. All right, now let's go up to 30 degrees. Same thing, you could advance it, frame by frame. I'm just going to grab this, and I think I could do a pretty good job. So this has been rotated through about 30 degrees, right, from here to here. And I've got 0.90833. So same thing, 30 degrees. And then whatever this amount of time was, 0.90833, etc. So keep doing this until you populate this. At least 6. You can probably get 7 if you wanted to. And we are going to then graph, well, let me back up a step. Once you get delta theta here in degrees, we want to also put it into radians. I'll tell you how to do that in just a minute. And then once you have time, we want to have a column here for time squared. That'll make more sense in just a moment. And then what we're going to actually plot is delta theta on the vertical axis and time squared on the horizontal axis. Okay, so let's talk a little bit about the theory behind that. Okay, so this is basically our picture. I'm just representing this as a circle. Here's the mass here. Whoops, drawing's not the best, but you get the idea. So the string's wrapped around. We've got some tension in this cord. So the reason that we're looking at time squared, here's a rotational kinematics equation. Delta theta, initial angular velocity times time, plus 1/2 alpha t squared. And we're starting from rest, so this term is actually 0. So again, technically, we're going clockwise, which is the negative direction, but I'm just looking at the magnitude of the angular acceleration. Okay? So delta theta then is 1/2 alpha times t squared. And again, you have to start from the point where it just starts moving, then that's why that's 0. So if we're able to plot t squared versus delta theta, this is in slope-intercept form, right? So y is equal to mx plus b. So we've got this equation. This is just in general when you have x on the horizontal axis, y on the vertical axis, and that's really what I have here. This is on the vertical axis, and you'll see that this term is actually 0. So you can compare this to this. So whatever comes in front of x is the slope. This is the slope, right? That's what's coming in front of t squared, the horizontal variable here. So the slope turns out to be 1/2 alpha. So when you make your graph, the slope is 1/2 alpha. So when you put all your data in, graph it, the Pivot interactive program will tell you what the slope is, and you know it's equal to 1/2 alpha, so you can solve for alpha then. So what can you do with alpha? So remember Newton's second law for rotation. Actually, let me go back up here. So you know from before, F is equal to ma. That's the net force is equal to ma, and then you have to figure out, what are the actual forces. Now, the rotational version of Newton's second law is torque, tau in other words, is equal to I times alpha. So tau is the torque. This is the torque. This is the rotational inertia, moment of inertia, and then this is alpha. So you can kind of see the symmetry between these equations. F and torque are similar. Mass and rotational inertia are similar. And regular old acceleration is similar to angular acceleration. So from the dynamics part and from the graph, you can figure out what alpha is. The goal is to figure out eventually what this moment of inertia is. So from this equation, I have moment of inertia is torque divided by alpha. Okay, so from the graph, you get alpha. How are we going to get the torque? Let's look at the picture again. Okay, so here's a drawing of the wheel. You can notice at the top here, I call this the normal force. The wheel is actually connected with a bolt and a nut right through the center. That's what I'm just calling it, the normal force, really the normal force on the wheel from the bolt. That force does not make it rotate. It's really, the rotation is really due to the weight of the hanging mass. So the 20 grams there. That's the force applied here, a distance r from the center. I call it big R here. So again, technically, this weight force is making it, the torque provided by it would be negative because it would make it rotate in the clockwise direction. I'm just looking at the magnitude of the angular acceleration that we found from the graph and the magnitude of the torque. Okay, so the torque we have, again, that's tau. Rotational dynamics wise, it's equal to I times alpha, but physically it's force and then how far from the pivot point is the force. So really it's R times F times the sine of the angle between those, but here the weight force and the lever arm are perpendicular to each other, so we would have the sine of 90, which is 1. So the force we have is the weight, and the distance is just called big R. Good, so you can get the torque that way. mg times R. That's what the torque is. So you know the mass, that's 20 grams. Make sure you put it into kilograms. G is 9.8, and R is whatever you measure it to be. And again, make sure you put that into meters. The measuring device is in centimeters, so convert it to meters. So mass, make sure that's in kilograms. G, 9.8 meters per second squared, and then make sure you put this into meters. And then you can calculate the torque. So remember, the rotational inertia we're looking for is torque divided by alpha. Okay, so you get alpha from the graph. You can calculate the torque. You actually do that in the first part of the lab. You can calculate the torque because you know the force and you know the distance. So once you have both of those, put that together to figure out what I is. Okay, right here. Okay, excellent. Let's go back to the actual lab real quick. Okay, so here's the measuring device. Put it wherever you want to try to figure out what the radius is. Okay, looks like it's about 30 centimeters or so. Remember, turn that into meters. Okay, and again, you want to, right after you release it, and then before the mass hits here. And then you'll have to put the delta theta here into radians. Let's review how you go from degrees to radians. Okay, so if you go completely around the circle, all the way around, that's equal to 2 pi. Now, radians isn't really a unit, it's a label. So if I just did 360 as 2 pi, that's completely right. Typically what people do, though, they think about it as a unit. So if I wrote radians here, that would be okay. Just remember, it's really just a label, not really a unit. I'm showing you this because I want to show you how to convert degrees into radians. Okay, so if 360 degrees is 2 pi radians, I could divide both sides by 2 and divide both sides by pi, because I want to figure out, how I can actually convert these from one into the next. Okay, actually what I'm going to do is divide both sides by 360, and if I do that, I get 1 degree is 2 pi, again, radians over 360. So 1 degree turns out to be, is equal to pi over 180 in radians. So that's the conversion factor. So if you ever forget what it is, this is how I remember it. All the way around is 360, so that's 2 pi. So if you have a number measured in degrees, you could easily convert it into radians by multiplying it by pi over 180. That's the conversion factor. Okay, so the second column in our data table, we're going to have to use that idea. So let's actually do that together. So if you wanted to, you could do it manually. I'm going to do it like this. Let's see. I clicked up here, these 3 dots, change column formula. And I want to do delta theta times pi. Now you can, this is what I'm going to use for pi, 3.14159, and then divided by 180. Again, you don't have to do this. It's just going to save you a lot of time, though, if you do. Submit. Now look, these are automatically from degrees into radians. And then probably the next one I'm going to try to do is 45. Oh, see it appears there. 60, 75, going every 15. And you could even do, you can probably do one more. You can probably get about to 90 degrees if you wanted to. And then you actually have to do the measurements, figure out what these times are. Same thing with time squared. You could use the formula. Change column formula. I'll click that. I'll just do t times t, right? That's the same as t squared. And then those are populated for you. And then eventually you want to graph this. So you want to graph delta theta in radians and t squared over here. Just to remind you, you just click here. What do you want to graph? Pick whatever it is. It's actually the second delta theta because that's the one that's measured in radians. Okay, and you'll have a nice graph, and once you make the graph, it'll say what the slope is. So remember what we did before, what the slope actually represents and how much it actually is. And again, the very first part up here, this data table, is where you can figure out the torque. So measure the radius, you have the hanging mass, the weight is the mass times 9.8, as long as you do the mass in kilograms, and then you can calculate the torque just like we went through. Okay, so that's theoretically how you're going to be able to come up with the moment of inertia. Now we've made some assumptions, or we will make some assumptions. This shape we're going to assume is a thin hoop. You can see it's not really completely thin, and it also has some spokes. So in the table from chapter 7, let me scroll down here a little bit. Okay, we went through that part. This part here, find the theoretical moment of inertia. Let me show you what we're going to actually use. So the radius you would have had measured. Here's the mass of the one that we actually use, the spinnery GZ light. And this is in grams, so you have to turn it into kilograms. So we're going to approximate this as a thin hoop. Okay, let's go back and remember what the formula for that is. Okay, so when you look in the book, you'll see several different shapes. If we assume this is a thin hoop, the rotational inertia is the mass of the hoop times the radius squared. Now, in the lab, there's 2 different masses. There's the hanging mass. That's not the mass I'm talking about here. This is literally the mass of the actual rim, and that's the 670, whatever it was, in grams. So you can use that, and the radius. This is the theoretical moment of inertia. Theoretical. And what you're going to do is compare that to the experimental one. Remember, the experimental one you got from torque is equal to I alpha and then I is torque over alpha, where alpha comes from the graph, torque is mg, little mg times r. Okay, and you can compare those to each other. The theoretical way, you do that a little bit later in the lab. The first part of the lab is to get the experimental. Now you'll see they're not going to be the same. The biggest reason that they're not the same is the theoretical calculation here. We're assuming this is a thin hoop, and you can see that it's not. If we have spokes, how thin is the actual hoop? Well, it's not super thin. I mean, it's not really too big, but this is what we're using to calculate it. Maybe it should be slightly different. So if you get a percent difference between 20 to 25%, don't be surprised. There's a part to discuss why you think that happened. Why did you get such a large percent difference? Well, to me, the biggest reason is this theoretical moment of inertia. Okay, if you have any questions, just email your lab instructor. Have some fun with it, and hope to hear from you soon. Bye-bye.